Hi, I'm Meghna Pandey from TCS Innovation Labs Mumbai, which is located in Thane in India. I, along with Rupayan and Dr. Sunil, we are a team which works on emotion recognition in spontaneous speech. Today, I will be talking about my work in the paper named as Knowledge-Based Framework for Intelligent Emotion Recognition in Spontaneous Speech. To start with, I'll be starting with the introduction, in which I will be talking about the state-of-art technologies followed by the objectives. After the introduction, I'll be talking about the challenges and motivation, then our approach, wherein I'll be explaining the framework that we have used along with the scheme and technology, which will be followed by experimentations in details along with results and analysis, and then followed by the conclusion. So to start with the introduction, emotion recognition from speech. Emotion of a person given in a speech waveform, what we normally do is we do a feature extraction and then we give it to a classifier which will classify the emotion of the spoken speech as angry, happy, sad or neutral. We will be dealing with these four basic emotions for our work. To talk about the state of art conventional systems, we have used local features like pitch, energy, spectral, TEO based, and we have also extracted global features like mean, variance, maximum, minimum, skewness, kurtosis, etc. Feature types to be used depends on application, classification of scheme, etc. Classifiers. Classifiers are mostly data driven and statisticals like GMM, SVM, HMM, GMM, ANN, etc. Classifiers to be used depends on applications, data space and computational issues. Objective: to propose and design a generic emotion recognition framework that we can work for spontaneous speech and acted speech, to incorporate the knowledge regarding time lapse of the utterance in the audio call and context based information, to improve the recognition even in a training testing mismatch condition. Challenges and motivation. First, talking about the challenges. First challenge is to identify emotion in day-to-day conversation, that is spontaneous speech, is difficult. Human perception for emotion is better in acted speech compared to spontaneous speech. Emotions expressed in spontaneous speech is not prominent like in acted speech. So our motivation: emotion detection plays an important role in human-computer interaction. Human perception for emotion is better in acted speech compared to spontaneous speech. Acted speech exhibits better discrimination than spontaneous speech. Human annotators are better on spontaneous speech when the contexts are given. Primary challenge. As you can see in the graph, the acted speech exhibits better discrimination than spontaneous speech. Possibility of recognition error is more in spontaneous speech compared to acted speech. Along with the primary challenge, we have additional challenges like feature extraction and representation. There is no optimal feature set which can be used for non-acted or spontaneous speech. Acoustic variability like different speaking style, different speaking rates, different speakers, different sentences and semantics. Along with that, speaker genders like culture and environment. Frame durations, no agreement regarding the minimum or maximum time duration that exhibits an emotion. We did a small experimentation wherein we used an IVR call and we used around 13 utterances of the IVR call. These were given to the 7 annotators who were told to annotate the emotion of that particular utterance. If you see the first section of the table wherein we have given the kappa score without any knowledge to the human annotators, the kappa score we get around k is equals to 0.12, which shows that there is a very poor agreement between the annotators when they do an annotation. So we did the second part of the experiment wherein we used the knowledge. Knowledge was time-lapse information of the utterance and the linguistic content, what is being spoken in that particular utterance. When we use these two knowledge, you can see that the kappa score has increased to 0.65, which is a substantial agreement between the annotators. So we followed this approach. We designed a framework wherein to identify the emotion of a present segment, we use the information from the past spoken speech. Like if you want to identify the emotion of the present segments, what we need to do is we need to further split that segment into smaller duration frames or frame size of smaller duration, and then we do the emotion recognition. Along with that emotion recognition, we also have the information, that is the knowledge of the time-lapse information and the ASR plus voice analytics information. When we combine all this information together, we get a better emotion recognition. So to start with, we'll be talking about the emotion recognition system. So the emotion recognition system, X tau be the speech utterance whose emotion is to be determined, and let there be n possible emotions like E1 as angry, happy, sad, neutral associated with your speech utterance. Emotion at any point of the time tau for a classifier is defined by the equation epsilon k to the power pc is equals to probability of ek upon xt. Now talking about the time-lapse information, output score from an emotion recognizer are given as input to the knowledge-based system. This system modifies the score depending upon the time-lapse of the utterance in the audio signal. We hypothesize that intensity of some emotions, namely anger and sad, increase and some like happy decreases. The output can be represented as epsilon k to the power mc is equals to wk epsilon kq to the power pc, where epsilon kq is the probability score and wq is the weighted vector at the time q. Then talking about the ASR and the voice analysis. As you can see from the block diagram, the modified score of epsilon k is then fed to the knowledge-based system. ASR converts the previous spoken utterance to text. Text analytics generates a weighted vector WT that contains probability of emotion given by the spoken word or phrase. Observation. Spoken words from one speaker at any instant of time induce some specific emotion in other speaker during a call conversation. This knowledge-based system performs two tasks. One is speech to text conversion by ASR. Second is voice analytics. This is another experimentation that we carried out along with the IVR Ceres call. Ceres is speech-enabled railway enquiry system. Wherein if you see, we have an IVR call where is the system asked, welcome to the system. Then the system says to select a language, user says English. Then the system asks what functionality would you like to select. The user speaks out seat availability. The system says unable to understand. Second time the user again speaks out seat availability. Obviously when we are speaking for the second time we are more stressed out. But if you give the same utterances to a general emotion recognition system, what we get are the scores like K1, K2, K3 and K4. So if you see at the second seat availability wherein the emotion comes out to be as happy, but actually it is not happy. So when we incorporate these knowledge of time lapse and the linguistic information along with the weight, here the emotion changes to angry with a score of 1.2, which is correct. About the experimentations that we did, we used the spontaneous speech dataset details wherein we used IVR Ceres calls and some call center calls. So the total number of calls were like 117, both were telephonic calls for a Ceres as well as 210 for call center calls. Number of annotators to annotate these utterances were 7 for both IVR as well as call center calls. The average number of utterances per call were around 18 for the IVR and 27 for the call center call. So if you see the kappa score without any knowledge, for IVR it is 0.14, whereas for call center call it is 0.12. Now using substantial agreement by the kappa statistics. If you see, when we give this knowledge, the kappa score with the knowledge has changed from 0.14 to 0.68, which is a good agreement between the annotators. And for the call center call, it has increased better from 0.17 to 0.70. The average length of these call duration or this utterance duration was 3.1 second for IVR calls and around 11 seconds for the call center calls. Talking about the experimental details, we worked on the speech signals which were of k kHz 16-bit. We did no pre-processing to do any noise suppressions. Feature extractions were done using the OpenSmile toolkit, wherein we use 6 low-level descriptors like intensity, loudness, F0 envelope, LSF, MFCCs, ZCRs, along with 12 high-level descriptors up to 4th order statistics. With this, we used 384 dimensional features which were taken from the Interspeech 2009 Emotion Challenge, and then we did a feature selection to reduce the dimension. The classifiers which we have used for our experimentation was SVM, which was polynomial kernel, ANN, that is backpropagation for training, neurons in hidden layer optimized through experimentation, and KNN. The results are as follows. If you see, I have given the IVR series, that is spontaneous speech, along with the call center, which is also spontaneous speech, and EMODB, that is acted speech. If you see the classifiers, we have used SVM, ANN, KNN, and the combinations of all the 3 classifiers. Then in the description, we have provided the weights lambda p, that is the probability scores for the conventional system, along with M and T. M is the time-lapse information and T is the linguistic content. U and M, what it indicates is unmatched condition and matched condition. Unmatched condition is like wherein we have trained the system with the EMODB, that is acted speech, and tested on the spontaneous speech. And matched condition is we have trained the system with the, for IVR calls, with the IVR calls spoken speech itself and tested on the IVR speech, and for call center call we have trained the system with the call center utterances and tested on the call center utterances. So here you can see how the system has performed. For unmatched conditions, it has, for conventional baseline system, it has gone, for IVR calls it has gone from 35.3 to 37.8 to 36.8 for all the 3 classifiers. But when we combine all the 3 classifiers, it gives us a good performance of 40.2% accuracy. But to this, when we have added the time-lapse information, it has increased from 35 to 44.3, 48, then 62, and when we combine all the 3 classifiers to 72.9. Further, when we add the linguistic contents, it has improved to 79.1%. Now when we further add the time lapse as well as the linguistic content to the conventional baseline system, it has improved from 71.3% to 82.1% when we combine the output of all the 3 classifiers. Similarly, you can see for the call centers, wherein it has improved from 69.8% to 78.1% accuracy for emotion recognition. EMODB was used only for the training system, wherein the conventional baseline system, the accuracy came to around 87.3%. Conclusion: we observed spontaneous speech emotion recognition is difficult compared to acted speech. We hypothesized and proved that Lack of discrimination properties in the audio can be handled by associated knowledge regarding the linguistic content, time lapse of the utterance in the call. The main contribution to this paper was development of generic framework for spontaneous speech emotion recognition that can also be used for acted speech. The framework has been tested on 3 different data sets, 2 spontaneous and 1 acted, in both matched and unmatched train test condition. Classifier fusion plus knowledge incorporation performs best than conventional emotion recognition system, even in unmatched train test scenario. Thank you.